All right, welcome to this video. We're going to be talking about section 6.6, which is on logarithms. And it's a brand new type of function, brand new type of operation, if you want to call it that. I want to compare it to some things that we already know before introducing it. And those would be that we kind of know how to undo things, or let's say that we have facts that we can represent forward or backward. Let me just give you some examples. Let's say that we know 5 plus 2 is equal to 7. We also have a fact that would be 7 minus 2 is equal to 5. Okay, so those are sort of the blue one going forward, the red one going backward. Okay, we have 2 times 8 is 16. 2 times 8 is 16 is going forward. We can also say that like 16 divided by 8 is equal to 2. And then we have sort of like a backwards going thing. It's the same fact. It's the same times table, but in reverse. Now, better yet, we can say something like 3 cubed is equal to 27, but then the cube root of 27 is equal to 3. Again, all the same facts, or each column represents a separate fact that is represented by two different operations. I would call these operations inverse operations. So something like adding 2 and subtracting 2, they're inverses. Multiplying by 8 and dividing by 8, same deal. Cubing and taking a cube root, those are going to be inverse operations. So a logarithm is going to be the inverse operation to exponents, or exponentiation. All right, now to introduce this logarithm thing, this inverse of exponents. Again, let's compare it to something that we're somewhat familiar with. Something like, how about 2 times 5 is equal to 10? And its inverse, the inverse of multiplication is division. It would be something like 10 divided by 5 is equal to 2. And the way these work is the answer in one fact becomes part of the problem in another. So what we want as we look at this logarithm is a way to get the exponent to be the answer and the 64 to be part of the problem, if you will. Part of the expression is probably a better way to say it. And the way this is written, I'll use some of the same colors so that they kind of pop out. We are going to rewrite 4 to the third power equals 64 in its logarithmic form, or its inverse form, by saying log, okay, so literally an abbreviation for logarithm. The base of the exponent, the 4, is also called the base of the logarithm. It's going to be written like a subscript. The answer to the exponent problem is going to be in the problem here. So we would read this log base 4 of 64. And it has, this is an expression that has a value, and its value is the power of 4 that would create a 64. Once you get the hang of it, this is actually pretty understandable, but for the first time you see it, like anything new, you're going to be a little bit intimidated. So with the color scheme that we have here, let's also rewrite 2 to the 5th and 3 to the negative 2nd as logarithmic expressions. As we rewrite 2 to the 5th power, what I want to do is kind of start writing it. This would be, of course, log base 2 of 32. Now we're going to see problems like this, and we're going to be asked to evaluate them, or to simplify them, or to tell us what they're equivalent to. This is asking 2 to what power is equal to 32? Well, of course, we have that right over here, so this is going to be equivalent to 5. And what we're basically doing is creating those same facts, both forward and backwards. I would say on the left, we're going forwards. 2 to the 5th is equal to 32. And then on the right, going backwards, log base 2 of 32 is equal to 5. Following that same logic, if we rewrite 3 to the negative 2 is equal to 1/9. The base 3 is also the base of the logarithm. Log base 3 of 1/9. And to avoid ambiguity, I'm going to put it in parentheses here. That's going to be equal to a negative 2. All right, so if we take a look at our notes for this section, you can see the same examples that we just did, roughly the same color scheme present, but something that we haven't talked about yet is, well, if the exponent or if exponentiation and a logarithm are inverses, then their graphs should look like inverses, meaning that they are reflected across the line y equals x. And here we have a graph from Desmos where we have the green graph representing the exponential. It has all the important features of that, and now we are reflecting it. We're going to take, for sure, a closer look at the graph of the logarithmic function shortly, but right now I think we need to spend some time getting a feel for what the logarithms mean, how we can convert between those and exponentiation, and basically just becoming a little bit more fluent. This is still new to a majority of us. So if our goal is to become more fluent in logarithms, what we'll do is we'll just translate some stuff. I'm going to rewrite some of these in example 1. These are exponentials or exponential facts. We're going to rewrite them as logarithms. We're also going to do some from example 2 where we take a logarithm and rewrite it as an exponential. Again, just to become more comfortable with them. So I'm going to do a couple of them from each of those sets and then give you an opportunity to pause the video and try the rest of them on your own. And then I'll show you the answers. And if you have any questions on them, you can always send them to me, but we'll be back in class sooner than you know. So let's take a look at example B. We have 81 is equal to 3 to the 4th power, which is a true fact. And if I want to rewrite this as a logarithm, don't be scared that the exponential part, the 3 to the 4th power, is on the right side. That's not going to change anything. But all of our logarithms are going to have a log as part of them. You should make it a point to know that the base of the exponent is also going to always be the base of the logarithm. And then we kind of switch the answer and the exponent. So 81, which had previously been the simplified version of 3 to the 4th, is the argument, and the exponent 4 is going to be the answer. Let's also look at example D because it has fractions in them, and they can oftentimes just create just a barrier to understanding these, but it's kind of going to be the same. As long as this fact is true, which it is, we can say that log base 2/3 of the answer 8/27 is going to be equal to the exponent 3. After you write these, it's not the worst idea to try to kind of cover up the original problem and see if this makes sense. Maybe with the fraction that might be might not be the first place we want to try, but let's actually go back to this one. I'm going to take the answer out of frame, and now we have log base 3 of 81 is equal to 4. What this is saying is that base 3 to what power is equal to 81, and that power necessarily has to be 4. It is a true statement, and as we see more of these, they're going to start clicking. They're going to start making more sense. All right, here's example 2. And actually, I find that converting the logarithms into their exponential form is a little bit easier for 2 reasons. Number one, when we get an answer, it looks like something that's more familiar. So it's going to be less scary once we get it. And if it's correct, or if it's a factual expression or equation, then it's going to make us feel better. But also there's sort of like a visual way to do it. Let's dive into example A. Whenever I think of converting these, I always think of the recycle symbol It's like on the side of your recycling containers at home, I'm sure, but I'll put it on the screen. It looks like this. I always kind of replicate that when I'm rewriting these. And I start with the base 2 and say that 2 raised to the 4th power is equal to 16. Now, I know it's not a perfect recycle symbol, but it gets the point across. It's that idea, that circular idea, or in this case, triangular. But I can write that out as the base 2 raised to the 4th power is equal to 16. And like I said, once we get it written, it starts looking more familiar. Oh yeah, 2 to the 4th is 16. So I know I kind of rewrote it the correct way. You can use this to check your previous answers. Back on the previous page, we had said that 81 equals 3 to the 4th, letter B, can be rewritten as log base 3 of 81 equals 4. Well, I'm going to translate it back and see if I get the same thing I started with. 3 to the 4th power is equal to 81. Yes, 3 to the 4th power is equal to 81. All right, one more back in example 2. Let's look at example E, 2E. And again, it has a fraction in it, so it could be a little bit scary. Now, this is a true fact. Log base 7 of 1/49th is equal to -2. How does that make any sense? Again, it will once you get used to them. But for right now, let's do the recycle thing. 7 raised to the -2 power is equal to 1/49th. So how can we write this? Raised and equals. If those symbols help, if those words, those triggers help, let's go ahead and do that. We'll say 7 raised to the -2 power is equal to 1/49th. And yeah, that is true. The negative exponent would create the reciprocal 1/7, and when we square the 7, we get a 49. That should make sense. All right, let's see if you can get a handle on this. Take a second, pause the video, finish out the rest of the problems in examples 1 and 2. And I hope you're ready for the answers because here they come. I'll leave them up on the screen for a few more seconds and then we'll dive into example 3. All right, here we are at example 3. Here we're asked to evaluate the logarithms. So evaluate kind of just means for us, at least in this case, to simplify, to come up with a value that is a lot more simple than writing log base 4 of 64. And the way we're going to do this is kind of think about that. Well, think about the recycle symbol, but also think about, well, we're looking for an exponent. The answer to these problems is going to be an exponent. What I'll do for something like example A is I'll write out, this is supposed to be, and in fact, I could even put equals something, equals my answer, what it's supposed to be. And I could rewrite 4 raised to that power, that unknown power, is going to be equal to 64. When I think about it this way, well, it's pretty obvious that 4 cubed gives me 64. So log base 4 of 64 is equal to 3. And that is the answer. That's all we have to do. It's a matter of tricking our brains into getting us to do it. If we look at another one like log base 5 of 0.2, until we get used to it, we might decide to write things out this way and say 5 raised to that power, that unknown power, is going to be equal to 0.2. Now, for this one, we're not used to working with decimals, and quite frankly, I don't particularly like them anyway, except in certain circumstances. So I'm going to change 0.2 into its fractional equivalent, which happens to be 1/5. If you didn't know that off the top of your head, you can always convert it using, well, the way it's read. 0.2 is 2/10, or 2/10, which reduces by 2 to give us that 1/5. But now if we're asking 5 to what power gives us 1 over 5, that power needs to be a -1 so we get the reciprocal. So once again, take a moment or two to try to solve or simplify or evaluate examples B, C, E, and F. All right, once again, here's your answer warning. They are about to be on screen. Here they are. All right, we're back on the whiteboard to introduce the last topic that I want to cover in this video. And that is that, like most operations or most functions, there are a couple of defaults. Best example I have for you is the square root. You're taking the square root of 36, let's say. You don't need to write that the index is a 2. It's implied. Or when you have the value of, 2y plus x, well, you don't write it, but there's a 1 in front of it. Or even if I have, the value of x squared, I guess you could technically say there's like a +0, or if we're looking for a in fact, let's erase that. If I wanted to know y equals mx plus b, there's an implied 1 on the x and an implied 0 as the intercept. When it comes to logarithms, we know we might write something like log base 2 of 8 is equal to 3. If, however, you ever see log of 100, what that means is something that we'll call the common log, or the common logarithm. And the implied base is going to be a 10. So really, what power of 10 gives me 100? That's going to have to be 2. Okay, so that's one of them. The other one happens when we have a log base e. So if I were to write log base e, the value doesn't matter. We know e is like a tricky number to wrap our heads around. So I'm just going to put 20. We wouldn't write it as log base e. We have a special name for it, or a special notation for it, and that is ln of 20. So if you see that it's not written as the word log or the abbreviation log, it's ln, the implication there, what you should know is that it really represents a log with a base of e. Okay, those are kind of not interchangeable. Ln is the right one. Now you might first wonder, what is that? This represents the natural log. And like I said, it's abbreviated ln. I'm assuming this comes from like the Greeks or the Romans or something like that, like Logarithmus Naturalis or something to that effect. And that's why the letters are inverted, but it represents the natural log. Now, the biggest reason why we do this is because, well, number one, eventually we're going to be able to convert all logarithms into either common or natural logs, which is going to be really, really helpful because there are buttons on your calculator to handle common and natural logs. And in most cases, especially like the Texas Instrument calculators that we all come to know, you will find that there is a log and a natural log button. So in your notes, of course, you have pictures of what they would look like. I think that's from a TI-84. I have this calculator app on my tablet here that kind of mostly models it. So you can find out where they are by looking over here. And if you need help locating them on your calculator, obviously ask about them. But like everything else, this is new. So even though we just learned logarithms at the start of this video, seeing them now without a base, like we see in example 4, can be, again, like it's another wrinkle, it's another wrench to throw into this whole thing. So some of them we may be able to calculate without a calculator, and others we will absolutely need a calculator to figure out. Let's look at a couple right now. All right, example 4a is an example that we can evaluate without a calculator. So And the way we would do this is like understand that there's an implied 10 as the base. If we also put our little box there and rewrite using the recycle symbol to figure out what we're being asked for, 10 to what power is equal to 1,000? 10 to what power is equal to 1,000? 10 to the first is 10, 10 squared is 100, 10 cubed is 1,000. So this one becomes just 3. All right, I don't want to give it completely away, but example B is another one like this that we can solve without reaching for a calculator. Let's try one that we do need a calculator for using both the log and the natural log buttons. Those two examples would be example D and E. We're just going to need a calculator for this. So if I pull one up on the screen, again, if you have a different calculator, you may need to type things in a slightly different order. Make sure you understand how to use your calculator before getting in there to a test. But if I'm looking for example D, the log of 21 or the common log of 21, I can find my log button, which is here, and then just type in 21. Now, if this is all I'm asked to do, I could basically hit enter right here. I usually make a habit of closing the parentheses so that later down the line when the expressions are more complicated, I don't need to develop that habit. But I'm going to hit enter, and that gives me a value of approximately 1.322. And I'm going to say these ought to be carried out to at least 3 or 4 different places. You'll notice that they become really, really close when we're dealing with these logs. Now, if I want to handle the natural log of 8, again, it's asking e to what power gives me 8. It's not going to be a nice round number. So I'm going to hit the natural log button. This time it's next to the 4 and drop in the 8, close my parentheses and hit enter. And I'm getting about 2.079 if I go to 3 places. Now, once again, I'd like to ask you to attempt the rest of these. Example 4, some of them are going to be able to be done without a calculator, and some of them you're going to need it. I would like you to try to first figure out which ones you can do without a calculator. I will let you know in a moment, but then when you do need a calculator, go ahead and reach for it. All right, answers incoming. Here we are. Anything that I wrote out in orange can be done without a calculator. And I rewrote it using that recycle thing. I'm looking for the exponent. I think the tricky one is actually, it's tricky because it's too easy. That's example G. It's asking an invisible base e to what power gives me e squared. And I think once you write it out, you're like, oh, well, it's a 2. Like it's going to match the expression on the right side of that equation. Examples F, H, and I all require a calculator. They're not powers of 10. They're not powers of E. And one that I want to draw your attention to is letter H. Yeah, I stole the phone number from that song, but we have a large number, like 8,675,309, or 8675309. The common log of 8 million and change is only 6.9383. And that kind of explains how this is an inverse. One of the defining characteristics of an exponent or an exponential is that these things explode. We've used that word in class. They rise really quickly. Here are logs. They're going to get compressed really, really, really quickly. And that's why this one, for a really, really large number, we're getting 6.9383. And one last little example that we might come across problems like this is just, what if we don't have a calculator and we can't find an exact value? We should be able to estimate the value of a log between what we'll call 2 consecutive integers. Integers are, positive and negative whole numbers, and consecutive just means they're next to one another. So I would say example A is that between 5 and 6, or is it between 6 and 7, or is it between -2 and -1? So I'm looking for 2 values that it should be between. In the case of example A, I'm looking for powers of 3. Oops. I'm looking for powers of 3 such that the value of 25 is in the middle. And the two values that are going to work for me are 3 squared and 3 cubed. 3 squared is 9 and 3 cubed is 27. And like you can see, 25 is smack dab in between them. So what I'm going to say is, because these are my two numbers, log base 3 of 25 is between 2 and 3. So if we're being fair, you may need a calculator to find some of these larger powers, but don't use the log button as you solve these. Go ahead, take a moment and try B and C and D and E. I will do one more example with you and show you the rest of the answers as well. Okay, so the answers are here. And I'll actually explain two of them. Example B shows how we can use higher powers. I'm using 2 to the 6th and 2 to the 7th, 64 and 128 respectively, and saying that 75 is in between those. So log base 2 of 75 should be 6 point something. It should be between 6 and 7. C and E, and well, actually C, D, and E are all between 2 and 3. But focusing in on D, yeah, if you don't know your powers of E approximately, I totally understand. I did probably grab a calculator just to make sure I had the right decimal values, but E squared is about 7.4 and E cubed is about 20.1, so 17 is between those two. The natural log of 17 is between 2 and 3. So depending on how we're pacing out our work, this is the point where you can take a break and do a couple of homework problems. You should be able to do questions from 1 to 18 with as much as we've gone through so far. We'll pick up in the next video and talk about some properties of these logarithms. But until then, you could do 1 to 18, and I'll see you in the next video.